point, but the absolute max has to be the exact point at the highest.
Okay, I want to hear from some other folks. What do you got?
Relative max has to be like, the thing has to change from positive.
It's not the word it, that's better.
Function.
The function, how does it change?
From increasing to decreasing.
A relative max, you have a change from increasing to decreasing. An absolute max, what makes an absolute max an absolute max?
Is because it's at a certain point of when it's
It's the highest point on the graph. We cannot deal with the infinities when it comes to absolute max or relative max. So relative max, still the same thing. Absolute max, highest point. All right, question number 2. What's the difference between a global minimum and an absolute minimum? Oh, I need some more hands than this. What's the difference between an absolute minimum and a global minimum? Go for it.
There is no difference.
There is no difference. It's 2 ways to say the same darn thing. Question number 3. Do all continuous functions have an absolute max and an absolute min? All continuous functions. How many guys would agree all continuous functions have an absolute max and an absolute min? Okay, how many guys would disagree? All continuous functions have an absolute max and an absolute min. Adriana, why do you disagree?
Because if it's continuous, like it could be approaching, the function could be approaching infinity. So
Good
there's
save.
No absolute max.
Right, so for example, the parabola is a continuous function, right?
Yes.
And there's an absolute maximum?
Nope.
No absolute maximum. Jose, why?
Because you go to infinity.
Because we're heading off to infinity, right? You cannot use infinities. All right, yes.
So if those 2 arrows were changed to endpoints,
Yep.
can a graph have 2 absolute maximums?
And absolutely, but that's also why we often talk about absolute maximums and absolute minimums on a closed interval, so that instead of allowing going off to infinity, you're trapping it on an interval. This is the big deal with the limits of integration. Sorry, that's Calc BC, limits of integration. Endpoints. Endpoints.
What?
There he is.
All right, number 4. Can a function have a relative max, which is number 4. On a closed interval, will all functions have an absolute max and an absolute min? All functions will have an absolute max and an absolute min on a continuous on a closed interval?
Yes.
Say continuous.
No one wants to disagree. No one wants to disagree with this statement, David.
Even though there's still a line that doesn't have a maximum.
Okay, y equals x, but the thing is, I'm now saying on a closed interval. So put your blinders on. Is there an absolute max?
Yes.
Yes, over here. Is there an absolute min?
Of course.
Of course, over here. So all functions on a closed interval have an absolute max and an absolute min?
No.
Yeah.
Oh yeah, I mean yes.
Of course.
No! No!
Oh, it has to be continuous.
No! You fell for it. 20 of you fell for it, but not Adriana.
That was the example.
What do you have graph?
What the issue is, think discontinuous functions. Like the graph of y equals 1 over x. If I consider the graph of y equals 1 over x on this closed interval, there is no absolute max. Daisy, why is there no absolute max on this interval? But there's no absolute max because the graph heads off to infinity. Right? You've got a vertical asymptote. That messes everything up for us. There is no absolute max here. There is no highest point. There is no absolute min. There is no lowest point. However, the extreme value theorem, this is the part I want to make sure that you get down. The extreme value theorem says there's always an absolute max and an absolute min if 2 things happen.
Ooh, better.
You gotta get both. You gotta get both. Daisy, what are the 2 things? The function has to be continuous, right? This guy's not continuous. The second thing? It has to be on a closed interval. If you get both, then you are promised an absolute max and an absolute min. I'll throw one over here, and one over here, and another one over there. All right. Moving on. Where do you go?
Y'all should have just seen the chaos that's going on.
So we've got about 17 minutes, and if all goes well, we're going to get through one problem. We're going to get through one problem. Okay.
That's nice.
So I will tell you, you guys don't know this, but I'm trying to set you up for excellence because tomorrow we hit the world of optimization. It's word problems, it's geometry. The word problems are going to be the challenge. I don't want this part to be the challenge. So I got some emails last night from folks that said, okay, I don't quite understand the process. Why do we go through and do these things? So if I've got a function, so any function, here's some function. Does this function have an absolute max and an absolute min?
Yeah, we don't really get an endpoint. No. Is there-
This function
No, it doesn't.
does not have an absolute max because we go to infinity. Doesn't have an absolute min because we go down towards negative infinity. But once I put my blinders on, once I say on a closed interval, is there an absolute max and an absolute min?
Yes.
Yes. And the absolute max can happen in only 2 places, 3 places, depending on how you count. Your options are endpoints, right? So we always look at our endpoints. And the second is what I called yesterday, was it the internal candidates?
Yeah.
And I think this is where I lost some of you guys. I think everyone's fine with the endpoints. You're like, yeah, okay. But the reason we look at the internal candidates, we look for where I have a relative max. And I look for relative min. And the way I find those internal candidates is I look to see where is the derivative 0 or where is the derivative undefined. Where does the derivative does not exist? We always check the endpoints. That's the part that seems to make sense. But the hard calculus comes in with those internal candidates. We're okay? If I say f prime of x equals 0, horizontal tangent line, great. But could I be talking about this function? Could I be talking about absolute max and absolute min for this function?
Yes.
I mean, who knows? It could be any function. And if all I do is if I look for where the derivative is equal to 0, I'm only going to be considering these smooth kinds. I have to capture the cusp point kind of relative max or relative min. So this is where we look for f prime of x to not exist. When you're looking on the inside, you set the derivative equal to 0 and you figure out where the derivative does not exist. This is the big thing. This is going to be where you do 80% of your work. We're mostly okay? All right, so let's go hunting for some bear, shall we? If we're lucky, this one problem will fit in the space. All right, determine the absolute maximum minimum values of f of x equals natural log of x on this interval. Yes, ma'am.
Referring back to the graph on the right,
Yep.
how do you know if that's, like, say you just have the equation, how do you know that's a constant?
That's, you would, if all you had was, great question, if you had the equation but not the graph, how would you figure out cusp point? By finding the derivative and figuring out where the derivative does not exist. That's how you would do it, because you don't have a graph to see. You would capture it this way. Yeah.
And most of the time, for when we're looking for it does not exist, that means there'd have to be some type of like denominator.
There's going to be some denominator action happening that's causing the derivative to not exist. Jennifer.
So there's not a denominator, there's not going to be a...
Right, I got some emails last night, like the first couple of problems you did were polynomials, and it was like, but wait, where's the derivative undefined? Never. There were no denominators. There was nothing that was going to cause that problem to be undefined. All right, so let's take a gander at this one. We've got the graph of f of x equals natural log of x on the closed interval 1, 3. I've got a function. I've got a closed interval. Great, so I know my endpoints. My endpoints are going to be x equals 1 and x equals 3. Now with your class, I think after we did the endpoints, we said let's do the evaluation step. I want to let go of that. I want to go for those internal candidates. Tell somebody near you, how are you going to find those internal candidates? How do you find them?
Plug it into
The inside candidates. What do we do? No, Amy, how do we find the internal candidates?
you equal the factor derivative to 0?
You're going to set the derivative equal to 0. That'll get you some of them.
Oh, and equal to does not exist.
And you've got to consider where the derivative Does not exist. You gotta go for both. So, clearly, your next move, Abraham, is gonna be to do what?
I would set them like factor and then set it equal to 0. To get the candidates. Well,
I would hope you would want to do something else first. If I want to figure out where the derivative is equal to 0 and I want to figure out where the derivative doesn't exist, wouldn't it be helpful if I knew what the derivative was?
yes.
Okay, so go find the derivative. Go find the derivative. So f of x equals natural log of x over x. I want you to find the derivative. Everybody knows how to find this derivative. This guy here has to be quotient rule. So a little low, a little d high, minus a little high, minus a d low, over low low. Give me a quick thumbs up if you've got that as your derivative. X times 1 over x minus natural log of x times 1 over x squared. Okay. Got some points already. Now, normally, I would just tell you guys, hey, don't simplify. But here's the problem. I want to figure out where the derivative is equal to 0. I want to figure out where the derivative doesn't exist. You're going to have to do some simplifying. So be safe, be careful, do things that you know are right. Like, for example, x times 1 over x. X times 1 over x is 1. Natural log of x times 1. That's just the natural log of x. That's over x squared. This is my derivative. I'm going to consider two cases. I want to consider where does the derivative equal 0. And I want to consider where the derivative does not exist. I've got a fraction. Right? Don't overthink this part. You've got a fraction. If a fraction is equal to 0, the thing that you know for sure, hold on, Robert. You've got a fraction, you've got a numerator, you've got a denominator. If this whole fraction is equal to 0, the thing that we know for sure? Jose, what do you know for sure? The top must be equal to 0. Great, so I'm only going to figure out where is 1 minus the natural log of x equal to 0. Because I'm trying to figure out derivative equal to 0. If I want to try to tackle this at the same time, I'm going to say where is the derivative does not exist. And that means we're going to focus on the denominator. So I'm going to have to answer the question, where is x squared equal to 0? This guy over here, I can add natural log of x to both sides if you want to. If 1's equal to the natural log of x, maybe you know this off the top of your head. Maybe.
Natural log of 1.
Or maybe you look over there.
It's 0.
Oh God, oh God. Not natural log of 1. I want the natural log of something that's equal to 1.
Oh.
It's e. The other way you could do it is you can exponentiate both sides, and you get x equals e. Over here, if you get this one wrong, I will make fun of you.
It's 5.
Yeah, 5. Okay. My internal candidates are 0 and e. These aren't absolute max and absolute min. They're not even necessarily relative max and relative min. They are candidates. Candidates. I want to use that word carefully because it just means I could have. These guys here are candidates. So not done, but gosh, we're close. Before we go anywhere else, we're good with the endpoints? Endpoints are easy. Finding the derivative was okay?
Yep.
Setting it equal to 0, figuring out undefined. Good. So the only thing left is to figure out which one gets you the biggest y value and which one gets you the lowest y value. So how are we going to figure that out? You're going to plug in to the original one. Now, if you're going way too fast, like I just was here, you're going to make a mistake. How many internal candidates?
2.
How many internal candidates?
There's only 1.
There's 3.
2, 1,
It's
or
double
3?
rolled there.
Let me ask the question again. How many internal candidates, Jonathan? Because?
There's 2.
Look at the domain restriction. You only want to look from 1 to 3.
Wait,
So the one that you're going to get rid of
0.
X equals 0 for this problem with these domain restrictions is not an internal candidate. X equals E is the only internal candidate, and we still have endpoints. So now the last thing is you're on the evaluate step, and this is, oh gosh, I love this part.
Me too.
So evaluate. Plug in. X equals 1, X equals E, X equals 3. At X equals 1, I've got the natural log of 1 over 1. Natural log of 1, last time I checked, is 0. 0 divided by 1 is 0. If X equals E, I've got the natural log of E over E,
1 over E.
which is 1 over E. And now I've got the natural log of 3 over 3. I think we have a problem. No, we didn't mess up. I think we have a problem. You don't actually know what these are as decimals. Now, last night on the homework, I said it was totally legal to plug these values into your calculator, and that was fine. There was one that was like 4 minus the natural log of 2, and you, I don't know, plug it into the calculator. Would everybody agree? Plugging into the calculator would be a very easy way to figure this out. Okay, you can't do that. I have high expectations.
Box that.
Is there anything about those values that anyone knows for sure? Anything that anyone knows for sure? Jose, you think you know something for sure? Jonathan, Anthony, you think you know something for sure? What do you think you know for sure? Oh, okay, so if you're thinking about like growth rates, that could help. Other things that we know for sure about these values.
I mean, we know what E equals.
You know what E is equal to. E is 2.718. Good luck figuring out what 1 divided by 2.718 is without your calculator.
Can we just say that it'll be less than 1? Oh, but
Okay.
then we need to find the next.
So if this is less than 1, which it is, you don't know what this is. But I do know one thing for sure. I would hope everyone's okay that this guy over here must be positive. Is everybody okay with that? Natural log of 3 divided by 3?
No.
Smaller than
All of them are
It would still be
It'll still be positive.
Natural log of 3 is still positive. If that is all that you know, if that is the only thing that you know for sure, okay, I can deal with this. But that means you know something now for sure. You either know the absolute maximum or you know the absolute minimum. Look at those 3 values. Look at your choices. My choices are 0, 1 over E, and natural log of 3 over 3. I see 2 people that know something for sure, 3 people, maybe 4 people. What do you know for sure, Noemi?
That X equals 1, that's your min.
This guy over here is, it's what again?
Your absolute minimum.
It's the absolute minimum because?
It's less than or equal to 0?
Well, it's actually equal to 0. If this guy's positive and this guy's positive and this guy's 0, doesn't this have to be the smallest value?
yes.
Absolutely. Now here's what you're going to have to do. To finish this off, you get to do a little number line test action. Oh, so excited. So excited. So here comes my number line. It's been a while. Here's F prime. I'm going to put on my number line x equals 1 because that's an endpoint. X equals 3, that's an endpoint. And x equals e, which is right over here. At x equals e, the derivative is equal to 0. That's how we found that internal candidate. We set the numerator equal to 0. I'm not going to even think about anything bigger than 3 or anything less than 1. Not going to think about it. Not going to think about it at all. All I care about are the signs, the SIGNs. So what I want to do is I want to pick a test point. Pick some nice convenient number between 1 and e.
2.
No.
Some nice convenient number between 1 and e.
1.1.
Okay, not necessarily convenient, but okay. If e is 2.718, you could use 1.1, you could use 1.5, you could use 2. Now, what you do with the 2 is important. What you're going to do with the 2 is go back to the derivative. You're going to look at the sign of the derivative here. So if I find f prime of 2, that's what, 1 minus the natural log of 2 over 2 squared? Right, I'm just plugging back into my derivative. If you know what the graph of the natural log of x looks like, then you know what the answer to this is. If you don't know, because we've only got 2 minutes left, the graph of the natural log of x looks like that. There are 2 points you need to know on this parent function. One of them is the root. If x equals 1, the y value is equal to 0. The other one is that when x equals e, the y value is equal to 1. You've got an increasing function. If 2 is in between 1 and e, then the natural log of 2?
Is less than.
It's positive.
The natural log of 2 has to be less than 1.
Oh, yeah.
It has to be less than 1. This guy here is less than 1. And that's helpful because now I've got 1 minus less than 1, which is some positive number. So I'm positive on this interval. If I pick something bigger than e, like if I said, hey, how about f prime of 3? Now I've got 1 minus the natural log of 3 over 3 squared. 3 is a little bit bigger than e. The natural log of 3 is therefore bigger than 1. 1 minus the natural log of 3 has to be negative. Okay, so hold on real quick. From 1 to e, my function is
Increasing.
this is f prime.
So,
So f is increasing. Over here, f is decreasing. Look at your choices here. Which one's bigger? The value at x equals e or the value at x equals 3? What's the function doing? From 1 until e, your function has to increase. From e down to over to 3, the function decreases. Which of these is bigger? This has to be bigger because your function decreases once it leaves e. So this guy here has to be your absolute max. All right. So tonight's homework is on the back.